8 Awesome application of diodes in circuits. Diodes are electronic components that allow current to flow in one direction while blocking it in the other direction. They have a wide range of applications in electronic circuits. Here are 8 awesome applications of diodes. Rectification is one of the fundamental and important applications of diodes in electronics. It refers to the process of converting alternating current, AC, into direct current, DC, by allowing current to flow in only one direction while blocking it in the reverse direction. This is typically achieved using a diode or a combination of diodes in a rectifier circuit. Here's how rectification works. AC voltage input. The input to a rectification circuit is typically an AC voltage source, such as the output of a transformer or the mains electricity supply. Diode bridge rectifier. In most rectifier circuits, a diode bridge rectifier is used. It consists of 4 diodes arranged in a bridge configuration, which allows the conversion of both halves of the AC waveform into DC. Half-wave or full-wave rectification. Depending on the configuration, the rectifier can perform either half-wave or full-wave rectification. In half-wave rectification, only one half of the AC waveform, either the positive or negative half, is converted into DC, resulting in a pulsating DC output. In full-wave rectification, both the positive and negative halves of the AC waveform are converted into DC, resulting in a smoother DC output with less ripple. Filtering. To obtain a more constant DC voltage, a filter capacitor may be added after the rectifier to reduce the ripple in the output. This capacitor smoothens the rectified voltage. Rectification is a crucial process in power supplies and battery chargers, as it ensures that electronic devices receive a stable and continuous source of DC power from the often variable and alternating voltage sources in the electrical grid. It is a fundamental application of diodes in electronics, allowing devices to operate on the type of voltage they require. Voltage regulation is an important application of diodes in electronics, specifically through the use of Zener diodes. Voltage regulation involves maintaining a stable and constant output voltage across a load despite variations in the input voltage or current. Zener diodes, specifically designed for voltage regulation, exhibit a unique electrical behavior known as the Zener effect or Zener breakdown. Here's how voltage regulation using Zener diodes works. Zener diode characteristics. Zener diodes are designed to operate in the reverse biased mode, meaning the voltage across the diode is applied in the opposite direction of its normal forward biased operation. Under reverse bias, Zener diodes exhibit a very sharp breakdown voltage characteristic. When the reverse voltage across the diode reaches its specified Zener voltage, Vz, it starts conducting and maintains a relatively constant voltage drop, Vz, across its terminals. Voltage reference. Zener diodes are used as voltage references in electronic circuits. By selecting a Zener diode with a specific Zener voltage, e.g., 5.1 V or 12 V, you can establish a stable reference voltage. Voltage regulation. To regulate the output voltage in a circuit, a Zener diode is connected in parallel with the load, with its anode connected to the power supply and its cathode connected to the load. When the input voltage increases beyond the Zener voltage, the Zener diode conducts, effectively clamping the output voltage to its Zener voltage. This keeps the output voltage relatively constant. Load variations. Even if the load current varies, the Zener diode maintains a nearly constant voltage across the load, making it suitable for applications where a stable reference voltage is required. Voltage regulation using Zener diodes is widely used in power supplies, voltage references, and voltage monitoring circuits. It ensures that sensitive electronic components receive a consistent and reliable voltage, which is crucial for proper operation and protection against voltage fluctuations. Clipping and clamping are two common applications of diodes in electronic circuits, and they are often used in signal processing and waveform shaping. Let's explore these concepts. Clipping. Purpose. Clipping is used to limit the amplitude of a signal by removing or clipping off portions of the waveform that exceed a specified threshold. Circuit configuration. In a diode clipping circuit, one or more diodes are placed in series with the input signal. The diode conducts and allows the signal to pass through only when the signal voltage is within a certain range, determined by the diode's forward voltage drop. Types of clipping. Positive clipping, diodes clip the positive half of the signal, resulting in an output signal that doesn't go above a certain voltage. Negative clipping, diodes clip the negative half of the signal, causing the output signal not to go below a certain voltage. Bidirectional clipping, diodes clip both positive and negative excursions of the signal. Applications, clipping is used in audio applications, waveform shaping, and signal protection. It can be employed to create special audio effects or to protect sensitive components from voltage spikes. Clamping. Purpose, clamping is used to shift the entire waveform to a desired DC level or voltage offset while maintaining its shape. Circuit configuration. In a diode clamping circuit, a diode is connected in parallel with the input signal, and a DC voltage source, biasing voltage, is used. The diode conducts when the input signal goes below or above the biasing voltage, effectively shifting the entire waveform up or down. Types of clamping. Positive clamping, the diode clamps the waveform to a positive voltage level relative to the biasing voltage. Negative clamping, the diode clamps the waveform to a negative voltage level relative to the biasing voltage. Dual clamping, two diodes can be used to clamp both the upper and lower limits of the waveform. Applications, clamping is useful in video signal processing, DC restoration in communication systems, and in circuits that require precise voltage levels for further processing. In both clipping and clamping, the choice of diode and the circuit configuration determine the specific characteristics and behavior of the output signal. These techniques are valuable tools for shaping and controlling signal waveforms in various electronic applications. Signal demodulation is the process of extracting the original information signal from a modulated carrier signal. Diodes play a crucial role in demodulation, particularly in amplitude modulation, AM, and pulse amplitude modulation, PAM, demodulation techniques. Let's focus on AM signal demodulation. Amplitude modulation, AM, signal demodulation. Overview. In AM, the amplitude of a high-frequency carrier signal is varied in proportion to the instantaneous amplitude of a lower-frequency information signal, audio signal. The objective of demodulation is to recover the original information signal. Diode demodulator, envelope detector. Diode-based demodulators, known as envelope detectors, are commonly used in AM demodulation. Circuit configuration. A diode is placed in parallel with a resistor and capacitor, RC network. The diode is reverse biased, and the capacitor is connected in parallel with the load, usually a resistor connected to ground. The modulated AM signal is applied to the diode's input. The diode rectifies the AM signal, allowing only the positive envelope of the modulated waveform to pass through. The resistor and capacitor, RC network, smooth the rectified waveform to produce the envelope of the original information signal. Output. The output of the envelope detector is a waveform that represents the original information signal, which can then be further processed or sent to a speaker for audio reproduction. Applications. AM demodulation is used in AM radio receivers and communication systems. Diode-based envelope detectors are particularly effective in recovering audio signals from AM radio broadcasts. The diode demodulator works by rectifying the AM signal to produce a waveform that follows the envelope of the carrier signal. This envelope waveform represents the variations in the original information signal. While diode-based envelope detectors are simple and effective for AM demodulation, they may introduce distortion and require additional filtering to improve signal quality in practical applications. Diodes are commonly used in electronic circuits for various protection purposes, safeguarding components and systems from undesired electrical events and conditions. Here are a few key applications of diodes in protection circuits. Reverse voltage protection. Diodes are often used in reverse voltage protection circuits to prevent damage to sensitive electronic components. Placing a diode in series with the circuit blocks any reverse voltage that could harm the device. Overvoltage protection. Clamping diodes. Zener diodes or transient voltage suppressor, TVS, diodes are used to protect against voltage spikes or transient overvoltage events. When the voltage exceeds a certain threshold, the diode conducts and diverts the excess energy away from the protected circuit, preventing damage. Current limiting. In circuits where it's important to limit the current to protect components, diodes can be used in combination with resistors to create current limiting circuits. For example, using a diode in parallel with a resistor can limit current flow through a load. ESD protection. Diodes can be employed in electrostatic discharge (ESD) protection circuits to safeguard electronic components from static discharge events. These diodes are designed to clamp voltage spikes associated with ESD and divert the energy away from sensitive components. Flyback diodes. Freewheeling diodes in circuits with inductive loads such as relays, solenoids, or motors. Flyback diodes, also known as freewheeling diodes, are used to protect against voltage spikes that occur when the inductor's magnetic field collapses. These diodes provide a path for the inductive kickback current to circulate safely, preventing damage to the rest of the circuit. Protection against reverse current. In systems where backflow of current is not allowed, e.g., in solar panels or batteries, blocking diodes are used to prevent reverse current flow when there's a voltage differential in the opposite direction. Circuit isolation. Isolation diodes are used to prevent feedback into a circuit. They isolate one part of the circuit from another, which is especially useful in power supply designs. Fuse bypass protection. In situations where a fuse might blow due to inrush current when power is applied, a diode can be used to bypass the fuse temporarily, protecting the fuse and the circuit. This is often seen in equipment with large capacitors. Diodes play a crucial role in safeguarding electronic devices and circuits from various electrical anomalies, making them an integral part of protection strategies in electronic design and engineering. The specific type and configuration of diode used for protection depend on the nature of the potential threats and the requirements of the application. Signal mixing is a process in electronics where two or more signals are combined to create a new signal that represents some combination of the original signals. Diodes can be used in signal mixing circuits to achieve various signal processing tasks. Here are some aspects of signal mixing using diodes. Nonlinear behavior. Diodes exhibit nonlinear characteristics when operating in their forward-biased or reverse-biased regions. These nonlinear characteristics can be exploited in signal mixing circuits to create new signals. Ring modulation. In a ring modulation circuit, two input signals are combined using diodes. The diodes multiply the input signals, creating sum and difference frequencies in the output signal. Ring modulation is commonly used in audio processing to produce unique sound effects. Frequency mixing. Diodes can be used to mix two input signals of different frequencies, resulting in a signal that contains the sum and difference frequencies of the inputs. This is fundamental in radio receivers for heterodyne mixing to downconvert high-frequency signals to a more manageable intermediate frequency. Mixer circuits. Diodes are often employed in mixer circuits used in radio frequency, RF, and intermediate frequency, IF, stages of radio receivers. These circuits combine two signals to generate a signal with both sum and difference frequencies. Mixer circuits are essential for tuning and demodulating RF signals. Amplitude modulation, AM, detection. In AM radio receivers, diodes are used in the demodulation process to recover the original audio signal from the modulated carrier wave. This involves using diodes to rectify the carrier signal. Frequency doubling and halving. Diodes can be used to double or halve the frequency of an input signal. In frequency doubling, the diode operates as a frequency multiplier, producing harmonics of the input signal. In frequency halving, the diode clips the input signal, producing harmonics at half the input frequency. Phase-locked loops. PLL diodes are used in phase-locked loop circuits to mix and compare signals, allowing the PLL to generate an output signal that locks onto an input signal with a specific phase and frequency relationship. Signal mixing with diodes is a versatile technique used in a wide range of applications, from audio processing to RF communications. By manipulating the nonlinear characteristics of diodes, engineers and circuit designers can achieve various signal processing and modulation tasks, creating new and useful signals for specific applications. Voltage clipping, also known as voltage clipping or amplitude clipping, is a signal processing technique that uses diodes to limit the amplitude of a signal by clipping or chopping off portions of the waveform that exceed a certain voltage threshold. This technique is often used in electronic circuits to intentionally distort or shape the waveform for specific purposes, such as creating special audio effects or ensuring that a signal remains within a desired range. Here's how voltage clipping works in clipping circuits using diodes. Circuit configuration: in a voltage clipping circuit, diodes are placed in parallel with the signal path. The diodes are oriented in such a way that they are forward biased when the input signal exceeds a certain voltage threshold. Diode operation: when the amplitude of the input signal rises above the diode's forward voltage, also known as the diode's turn-on voltage, the diode begins to conduct and allows current to flow. Below this threshold voltage, the diode remains in the off state, blocking the current. Clipping action: as the signal voltage increases beyond the threshold, the diode effectively clips the waveform by limiting the amplitude of the signal. The portion of the signal above the diode's threshold is removed, resulting in a distorted output signal. Types of clipping. Positive clipping: in positive clipping, diodes are used to remove or clip the positive excursions of the signal that exceed the threshold voltage. Negative clipping: negative clipping removes or clips the negative excursions of the signal that fall below the threshold voltage. Bidirectional clipping: in bidirectional clipping, diodes are used to clip both the positive and negative excursions of the signal. Applications: voltage clipping is used in audio and music effects circuits, distortion pedals, and guitar amplifiers to create distortion and overdrive effects. It can also be used in video signal processing and communication systems to shape or limit signal amplitudes for specific purposes. The specific threshold voltage of the diodes and their arrangement in the circuit determine the characteristics of the clipping effect. By carefully selecting diode characteristics and circuit parameters, engineers and audio enthusiasts can achieve desired levels of distortion and signal shaping, leading to unique sound effects in audio applications. Light emission is another significant application of diodes, specifically in the form of light-emitting diodes, LEDs. LEDs are semiconductor devices that emit light when current flows through them in the forward bias direction. LEDs have a wide range of applications in lighting, displays, indicators, and optical communication. Here's a closer look at how diodes are used for light emission. Basic operation: LEDs are made of semiconductor materials, typically gallium arsenide, GaAs, or gallium phosphide, GaP, doped with specific impurities to create a p-n junction. When a voltage is applied across the p-n junction and current flows in the forward direction, electrons recombine with holes in the material, releasing energy in the form of photons. This process results in the emission of visible light. Color varieties: LEDs are available in various colors, including red, green, blue, yellow, white, and many others. The color of the emitted light is determined by the specific semiconductor material used and the impurities added to it. Applications. Indicator lights: LEDs are commonly used as indicator lights in various electronic devices, appliances, and machinery to signify the on-off status, operation mode, or fault conditions. Display technology: LEDs are used in displays such as 7-segment displays, dot matrix displays, and alphanumeric displays for numeric and alphanumeric character representation. Backlighting: LEDs are used as backlighting sources in LCD screens, including televisions, computer monitors, and mobile devices. Signage: LEDs are popular for outdoor and indoor signage due to their brightness, energy efficiency, and ability to create dynamic and eye-catching displays. Illumination: LEDs are used for general lighting in homes, offices, and industrial settings. They are energy efficient, have a long lifespan, and offer dimming capabilities. Optical fiber communication: in optical communication systems, LEDs are used as light sources to transmit data through optical fibers in short-range applications. Traffic lights: LEDs are used in traffic signals because of their high visibility, energy efficiency, and long life, reducing maintenance costs. Advantages: LEDs have several advantages, including high energy efficiency, long operational life, rapid response times, and the ability to produce specific colors. They are also more durable and have lower power consumption compared to traditional incandescent bulbs. Ongoing research and development efforts continue to improve LED technology, leading to higher brightness, increased efficiency, and new applications in fields like automotive lighting, horticultural lighting, and more. Light-emitting diodes have revolutionized various industries with their efficiency, versatility, and diverse color options. They have become an integral part of modern technology and lighting solutions. These are just a few of the many applications of diodes in electronic circuits. Diodes play a crucial role in a wide range of electronic devices and systems, making them a fundamental component in electrical engineering and electronics.